Welcome to lecture number 2 of module 3. In previous lecture, that is lecture number 1, we discussed the modeling of governing system, and now in this lecture I'll try to model the turbine as well as the generators, and so that we can see how we can control the frequency of the system and how the various loops are working in this ALFC, or you can say load frequency control. So to have this turbine model, as I discussed, we can have the steam turbines or we can have the water turbines, means the turbines which are used for the hydropower generators, that is called your hydro turbines. Here I have written this, and if we are using the steam as a energy flow medium, then it is called steam turbine. Steam turbine can have either reheater or without heater they can work. If it is without reheater, then we can write the steam turbine in a very simple transfer function, that is a GT. G is the transfer function and T denotes the turbine. In the S domain, I can say here it is a KT, that is a gain of the turbine, over 1 plus S TT, and this TT is the time constant of the turbine. And normally this TT is approximately, that is a line between 0.1 to 0.5 second. For hydro turbines, here the transfer function is slightly different, and here I can write the gain of the turbine is KT, that is multiplied by 1 minus 2 STW divided by 1 plus STW, and here TW is the time delay. Why this time delay is involved? Because the water is coming from very far end, it may be through the penstock and other things, and it will be having the time delay as well. But if your steam turbine is having the reheating facility, then we have to model that reheaters as well. So the turbine with the reheater, now what we can do, if it is having the reheat facility, means certainly your turbines will be having more than one stage, that it will have HP turbine, that is a high pressure turbine. Here I have written this rating of high pressure turbine, let us it is alpha. I am talking in the per unit system. Then if a total power rating of the turbine is unity, then I can say the rating of IP and LP stages is 1 minus alpha. So the total is 1 per unit. If you add alpha and 1 minus alpha, you will get unity, means the if total rating in the per unit is 1, then IP SP stage is having alpha per unit, then the remaining stages may have IP R and LP, it will be 1 minus alpha. So the time constant for the reheater, it is normally 4 to 10 seconds, because the steam from this outlet of HP will go to the boiler, and then after reheated it will be coming back to the IP and R LP stages. So it is a time travel involved, and that is normally 4 to 10 seconds. So static gain, again I have used the KT as the static gain of the turbine, and TT is the time constant of turbine that we have used here, you can see. So using all these, then we can have the time constant, or we can have the transfer function models. Again, this how the steam flow which is going, even though I explained in the previous lecture, that here you can say your HP turbine, that is high pressure turbine, here it is your intermediate pressure turbine, and here it is your low pressure turbines, and all these are connected on the same shaft, and it is coupled with your generator G here, that is called generator. So once you can see here the steam which is coming from the boiler, it is going to the HP, and you can see here the expansion process is done, and due to the expansion process this steam will do work, and that work will be in form of the rotation of the shaft. And after this is which is coming out, that steam after expansion, means it will release the energy which is in the steam, it will going back to the boiler again, and here it is basically reheated. And after once it is reheated, it is called the reheating process, and finally it is again here coming to your IP state, where again it is doing the work. Again here I want to mention that the output of this HP turbine is reheated, because the energy consumed in HP is very, very high, and then the steam which is coming out from the HP turbine, it is having low pressure and thus low temperature as well. So here there will be, if it is not reheated, there will be possibility that this steam will be converted to the water, and here, and that will damage the blade and the efficiency will be poor. So if you are reheating, then again we can utilize the remaining energy in terms of here IP and SP turbines. This IP here, again the steam is going out, and finally it is going to the LP here where expansion process taken place, and then after coming out from the LP, this steam is condensed. So we try to reduce the temperature. As you know, the temperature difference normally gives the work done. So here if T2 we can minimize, that is the T2. Here it is a T1 that relates the efficiency of this whole cycle, that is a steam cycle here. So we have the cooling towers, and we normally condense the steam, we convert it to the water, and this water is still having the high temperature. Now then we are having some pumps. Once it is condensed, then we are sending to HP heaters, because it is heated, because the energy which is coming out the boiler, it is heated here, and then this heated water is passed through the boiler, and there will be some leakage here. This demineralization water, normally it is called the dematerialized, there's no mineral is involved, otherwise that will damage the blade of the turbine. So here the leakage etc. will happening, some steam will be going out in the air, so that will be compensated by the DM water, and this water is combined together, and then we are using the BFP, that is called boiler feed pump. This boiler feed pump, again it is passing through the LP heater, because there are so many heaters stage, because the energy which is coming out from the boiler that is utilized, then we can increase the efficiency. To HP heaters and LP heaters are used, and then it is coming to your boiler. Here this in boiler it is heated, and that's steam. So this is basically a complete cycle with the reheating facility. Now to go for the derivation for the transfer function of the turbine with the reheating facility, here I can say that this HP part, the power output of this SP turbine, that can be related with the simple transfer function, that is a KT 1 plus ST, and then it is multiplied by, here you can say alpha term, and that is coming multiplied by the valve output. Means here this is your turbine, this is your change in the valve power, and here that is we are getting change in the PTH, that is a high pressure turbine. So this transfer function, because here we are using only the alpha times of that one, so here we are just multiplying alpha. Now for the LP and IP units power, here now 1 minus alpha is multiplied by this transfer function, because the remaining energy is going there, plus here there is some travel time, this TR, that is a reheating time constant TR, that is added here, and then it is your PV. So the total power means here the total turbine power is nothing but your change in the power here of your THP stage, and plus here change in your power at IP and LP stages. So here you can see this is this expression. So the total output of the turbine, including your various stages, will be the summation of all the power of the stages. So here your HP stage, here it is your LP and combination of your IP stage, that is intermediate pressure, low pressure and high pressure turbines. So if you add and then you can simplify, then you will find that KT 1 plus ST is common, here we can take, and then we can go for here now what we are getting, this stage here alpha plus I can say 1 minus alpha, here 1 plus STR, and this is simplified and we will get this here. So you can see we are getting a complex transfer function of the complete turbine which is having the reheating facility. To go for the simplicity, let us take it is not having the reheating facility. So only we have to ignore this, means we have to put alpha is equal to unity, means only SP part is there, means high pressure turbine is there. So this part here, this part will vanish. So we will have a simple turbine transfer function that is written here, and I have used the simple turbine without reheating facility. So it will come here this turbine model. This is the governor model, if you remember, which I derived in the lecture number 1. Now this PV which is coming, here what is happening, this your change in the PC is a change in the reference setting. Here change in the frequency, that is coming through the drooping characteristic with the negative sign. it is now coming to your governing, and governor is taking action. Whenever there is change in frequency or change in the power reference, this governor will act and it will try to change the input to the turbine, that is a steam, and that is your, you can say, valve power, that is a change in PV. And this PV, now it is steam power that is coming to the turbine, and finally it is giving the turbine power, or you can say rotational power, that is where your generator is connected. So now this is the model of your governing system, this model, this is your turbine model, and now this is going to your generator where generator is coupled, and we will see the generator model later on. Normally we try to make in such a fashion that the multiplication of Kg and Kt, here we normally keep it unity. Means if your governor Kg gain and here the turbine Kt, we normally design in such a fashion that we can make it unity. So what will happen now, the multiplication of this will be unity, and we will see in the later part as well. Now let us see, now keeping this Kt and your Kg is unity, we can write here this change in the power. Means from here, from this expression we can derive what will be this change in the turbine power by, in terms of, you can say, change in the reference setting and in terms of frequency setting, and we can write it a simple way, because this minus 1 upon R change in Fs, and that is multiplied by these two time constants, or you can say transfer functions. So here you can see that is what we are getting. This is the transfer function of governor, this is a transfer function of turbine, that is multiplied by the change in the reference setting minus change in the frequency divided by R, that is a regulation or constant slope, or you can say drooping characteristic. You will see that later on again. So we can write this is a complete this input output relation. So in this case, input is here a change in frequency and change in your reference power. Now to see this, the impact, or you can say the change in the steady state turbine output power, that is a change here I normally say this change in PTSS. The SS denotes the steady state condition. You know this final value theorem, if there is any change in any of the input, then as per final value theorem we can obtain the steady state value by limiting S tends to 0, multiplying S with this your output here, that is change in turbine power in S domain. So here once we are going for this and we are putting here, now we can get the steady state value of the turbine, that is a PTSS. First case, I am assuming there is no change in the frequency of the system and we want to change the output of the turbine by changing the step response. Means suddenly here you can see in this here the step change here time is changed and the reference setting is changed up to this magnitude. So this is the step input response. Just I want to know here this change now in the domain, you can say S domain, the change in the PCS will be nothing but for this one we know it is a change in PC, that magnitude here, this is your magnitude divided by S is your step response. So after putting this value here and putting your change in Fs is 0, so and putting S multiplied here, we can get this steady state value in the turbine output, that is we can see here what we are going to get here. We are to change it here, what we will get here S, and here this is this by S, so S will be cancelled and all this S term will be zeros here, 0 0. So we are going to get here this expression. So it shows that whenever you want to go for the steady state increase, means there is step input, it will be finally it will be settled to its power, turbine power will be increased. So when you are willing to increase the power, this steady state value will be increased. Of course we have the time constant, so it may require some times and it will settle down, but the final value will be change in PC. In another case, let us suppose I don't want to change the P reference, that is the PC, means I don't want to give raise or lower command. So, and frequency is changed, means suddenly if system frequency changes, and again I am talking about the step change in the frequency. Here again I can say this is your time, and change in the frequency here, that is your change in F. So this magnitude is changed. So I want to see how much the turbine output power is going to be changed during the steady state condition. Here suddenly change means there will be some settling transient, and finally it will be settled. So here what in this case, now this change in the PCS is 0, and we can put it 0, and we can get the expression from here. From this expression here we are getting change in the PTS will be 1 over this governing transfer function, here your turbine transfer function, and multiplied by change in F divided by SR, because here the change in F is here change in F divided by S, and R is already regulation. So again using your final value theorem in S domain, we can get this PTSS here, means we can get again this change in PTSS is nothing but limit S tends to 0 S into change in PTS. So using this we can get this expression final, that is with the change in the frequency. In this case we did not consider the change in the reference setting. So now you can see for change here the 0 means there is no change in the reference setting. The increase in turbine output power is directly proportional to the frequency drop. What I want to say, why it is drop, means here I am talking this increase, here I am talking drop, because the term where we are getting here is a negative. Means if your frequency falls down, the turbine output must increase to maintain the frequency, as we know. We require that, and this is giving that characteristic. So whenever there is an increase in the frequency, then turbine power must fall. Here the change in here is a positive, then change in the turbine output is negative. So it is a vice versa. So in other words, I can say if you are changing the frequency, you can say your system frequency increases, then your turbine power output will reduce. Or your this is reducing, then turbine power must increase to compensate the remaining energy, and therefore we can maintain the system frequency. In this expression here, you can see the R is appearing, and that is 1 over R, and that here it is called the droop of the governor. This characteristic is called the droop of governor, and normally the value of R is kept between 2 to 5%. I'll come to that point. What is the 2 to 5%? Basically the unit of R you can see here, it is nothing but, you can see the unit of R here, it is hertz per megawatt. Why? Here R will go here, means we can get here this R is nothing but your change in F divided by change in power. Of course it is a negative sign. So unit is not related to the plus and minus sign, but it related with the variables that are coming into the picture. So this is the frequency, this is your power, so it is hertz per megawatt is the unit in actual value. But in the percentage it is, we can write, again I'll come later part, we will see how that we can change from per unit to, means suppose one we are taking per unit, another is taking actual value, or both are we are taking per unit, here both are taking actual value, then we'll see that. So this here gives a relation that your change in frequency will be negative of the change in your the turbine output. So when power is increasing, frequency here it is increasing, what will happen? The frequency of the system will be changed accordingly. So the increase in the turbine power means system frequency falls, means the power must increase to compensate that. To see that, let us see one characteristic here. This characteristic is nothing but the droop characteristic, and here normally you can say this is the nominal frequency. In our case it is 50 hertz, and this is from 50 hertz to that we have increased to 1.05, means here it is 1 per unit, you can say. So this is the change in the frequency, and here change in the turbine output power, and this slope which is showing 1 upon minus r. So we have the family of curves. This is 1, here we have 2, here we have 3 curves and 4 curves. What does it shows? That here for 100% power, if this load is removed, if this load suddenly comes to 0, your frequency will be increased by 5%. So here frequency will become 1.05, means change will be here now your change will be 0.05 per unit. So this gives that if you are loading 100%, your frequency, if it is rated to 50 hertz, and if you are just changing, then again there will be change here with the 5%. Means now the load is reduced to 0. Now we are going to change in the frequency here is 0.05 multiplied by 50, means there will be change in 255 hertz in the frequency. So we have the family of curves. Again they are having the slopes. So now suppose you want to have this, what will be, if you are operating, that you are maintaining, controlling your frequency for 75% here of the loading. If you are increasing here, then how much you are going to get, how much now you can see this is the frequency which will be, if this value at this point, if you are reducing, then your how much frequency this increase just you are going for have. Means for 70% increase, here this will be your frequency increase. If you are for 50% here, your frequency increase will be this one, and for 0% you will getting this one. So this relates the loading of the turbine with the frequency, and again it depends upon this characteristic, that is a slope here, r, that is a very, very important. Now as I discussed, that's what is this, let's suppose r 0.05 per unit. As I said, the unit of r can be your hertz per megawatt, or it can be your hertz per unit megawatt. Means here the megawatt is in per unit. So just I am writing, because the per unit is very confusing, because per unit of hertz will be different than per unit of megawatt. So it is better to write the per unit megawatt, means power we are using in the per unit quantity. That we can also write here pu hertz over this pu megawatt, and this is called completely pu. Means your change in the frequency in the per unit here, and the per unit megawatt, it gives you per unit value. Now for this, let's suppose your base power is 100 megawatt and your frequency is 50 hertz, then r is equal to 0.05 per unit is nothing but we can write here 0.05 per unit hertz divided by per unit megawatt. Now we want to calculate in the actual value. So here 0.05. Now from per unit to actual value, we have to multiply by its the base value, and that is 50 hertz. Now we are getting here hertz divided by here hertz, that is a power 100, and now we are getting megawatt. So we are getting here 2.5 divided by 100 here, that is hertz per megawatt. So now this is the way of converting, and finally you can see this value just we are going to get 0.025 hertz per megawatt. So this is very, very important. You can say we started in the per unit 0.05, but this value has actual value is this one. Means if you are changing 1 megawatt power, here there is a change of 0.025 hertz in the system frequency. So if you are increasing, then it will be reducing. As I said, we had the relation that we are going to the change in here is minus r change in turbine power. So it is with the negative sign. So when you want to increase the turbine power, that is increase system frequency. Here if you are increasing, system frequency will increase, but we want that reverse action. So if the frequency falls down, this turbine will automatically try to increase this output, because here the R sign is there. So this is basically the concept for this R, that is a regulation. So we saw the combined effect of governor and turbine. modeling. Now let us model another very important component in this load frequency control, that is generator. So the generator modeling that consists here, we can now understand that this is your mechanical power or mechanical energy input through the turbine, which is rotating. Here this is rotating, so the torque is developed, and that is called the T mechanical torque. Now on the shaft, your electrical, that is a generator, is connected, which is giving output in terms of electrical energy. As you know, the turbine generator system is nothing but we are from mechanical energy, we are converting to the electrical energy. Although in the whole process, it is not only the mechanical energy is converted to electrical energy, but the fuel energy, that is a coal energy, or you can say water energy, that is in hydropower stations, that is coming to the turbine. So that energy is converted to the mechanical energy, and from mechanical energy we normally get to this electrical energy. So you can see this turbine torque T here, that is coming, this T mechanical, that is going in one direction here. This, let's suppose this rotating, trying to rotating, but the electrical, that is output, it will try to oppose, and that is basically the equilibrium condition. If this torque is in the same direction, what will happen? This will keep on accelerating and system will be out of step. So always at the steady state condition, when the T mechanical energy is equal to your electrical energy, in that case here this T mechanical will be equal to your the T electrical, and the speed of this rotating mass will be the constant. If there is a imbalance here, means if one quantity will increase, let's suppose the T mechanical is increasing more, what does it mean? That your mechanical energy is more than your electrical energy, this machine will try to accelerate. Means if your T mechanical is greater than T electrical, the speed of rotating body will increase. Why? Because this energy going output. Here output energy, input energy, some energy is here kept. As you know, the energy cannot be wasted. So as per energy conservation law, that energy is going from one form to another form. Means that mechanical energy, since it is more, we are getting less energy. So that energy is, mechanical energy is going to convert it into the rotational energy, and that is nothing but your kinetic energy. And that kinetic energy, you know, that speed will increase, and then speed is increased, and that's we have written here. Reverse is also true. If you are feeding less mechanical power, less mechanical energy, and your electrical output is more, then it is a reverse situation. Means you are drawing more power from this whole system. This is your complete system where rotating body is there. So if you are getting more, then what will happen? Whatever the energy which is stored in the system here, that will be coming out. Means the stored kinetic energy is released in the electrical energy, and this, if it is K is reduced, means the change in frequency will be reduced, and then frequency will fall. So in nutshell, I want to say that T mechanical, that torque, acts to increase the rotational speed. It will try, because input you are giving, it will try to increase. Whereas this T electrical will act to slow down the rotational speed, and thus it will do some work, and then electrical energy will be generated, and that is three-phase power that you are going to get. To model this, we have to have this rotating body concept, because there is some energy, that is input and output. It has some inertia, that is the inertia constant, I can say I, which I have used I is the inertia constant, and here it is rotating, that we have the angular speed omega. We will also use this angular acceleration alpha, because if there is any mismatch, there will be change in the omega, and this alpha is your angular acceleration. And now another term that is called m, means angular momentum, which is defined as the inertia constant multiplied by your speed, that is omega. So the basic relationship, just I want to derive, the T net is nothing but T net, I can say it is your T mechanical minus T electrical. Electrical means what is coming in and what is coming out, that difference is called T net. So, and that can be related with this here, this inertia constant I, multiplied by here the acceleration, that is the power. So this torque here multiplied by the acceleration and in inertia constant, that is related by the T net. Angular momentum already I derived. Here this m will be equal to your omega dot I. Now this P net, as you know, this torque, if it is multiplied by speed, then it will give the power. So the torque here and the power relationship with this expression. Now if we put the T net value from here, this first equation we can put here, and now we can use this omega into I here, this relation, so we can derive m into angular acceleration, that is alpha, will be nothing but your P net. Here we are talking all the values in actual quantity, you must remember this, because in the per unit this P net will be equal to T net. Here we are talking this P is in megawatt, this is in Newton meter, and this is in radian per second. So here everything here I am deriving in actual quantities. Later on we will convert to the per unit if you want to calculate in the per unit, otherwise you can also use in actual quantities. Now, so as I said, the T net is nothing but it is the T mechanical minus T electrical, and this is also called as the net accelerating torque, and sometimes people call it the TA. So TA, T net, in different books you will find the different names. So this is nothing but the difference in the input torque to the output torque. So that is the net which is inside the rotating mass, and that is called net accelerating torque. M is angular momentum of the machine. I, as I defined as the moment of inertia of machine. Alpha, that is a rotational acceleration in radian per second square, and omega is your rotational speed in radian per second. The difference in electrical and mechanical torque will cause to accelerate or decelerate. As I said, if TA is positive, then machine will accelerate, as already I discussed here, that here this concept is the difference here. If it is more, then it will accelerate, and if it is the difference is negative, then it will try to decelerate. So here the difference in the electrical and mechanical torque will cause to machine accelerate or decelerate. The speed of machine under acceleration will be, that is a omega naught plus what is your acceleration here, the rotational acceleration multiplied by time. So this will be your the speed of machine under the acceleration. If there is no acceleration, then the speed will be your omega naught. Omega naught is the base, or you can say constant speed, where both are balanced. The T mechanical is equal to your T electrical. So this relation is very widely used, and we'll see in the later part of this lecture. We also know that this omega is nothing but this here the phase angle of rotating machine is delta. Then we can relate this omega with your rate of change of angular phase angle, that is of rotating machine, or in other words I can say this delta is the integration of omega with respect to time. That's this relation. Now let us see here how we can. So now I want to calculate what is the change in the angular, or you can say phase angle of the rotating mass. Here what I want to derive, let's suppose this is your reference value, means you can talk with some any reference value, and here this is your rotating mass which is rotating. Normally in this rotating system, here if it is a reference, from here this is rotating, both are rotating with the same speed, then this angle is fixed and it is, you can say, locking a torque angle. But if this rotor will try to accelerate more, then this delta will try to increase, and this is also rotating, this is rotating at omega naught, or you can say at the synchronous speed. Both are normally in the steady state, they are operating at the synchronous speed, so that this torque will be, this delta angle is fixed. But if it is accelerating, what will happen? This angle will increase. If it is a decelerating, then this angle will decrease, and vice versa. So change in this angle, I can say this acceleration minus with their initial, that is the phase angle of the reference angle. So change in the delta that is here machine absolute phase angle here, that is we are going for this, minus with the reference angle, means absolute how much it has reached, and from this we can subtract, then we can get the change. So change in the phase angle is written as the integration of omega naught plus omega t, and this here we are into dt, and here basically I am sorry, this is alpha not omega. As I said, we wrote this expression, you remember this is your omega is nothing but your omega naught plus alpha t, which is I am using here, minus here that is a phase angle after reference angle here omega naught, or you can say synchronous speed. So if you are integrating here, you will get omega naught t, because this is a constant, so this t term will be appearing. Here alpha is constant, so only in the case it is a constant. If it is a changing alpha, then it is different. So we have to, alpha is also changing. We are assuming this alpha is constant. So this alpha here now t, so t square upon 2 will be there, minus omega naught t here, that we can get it. So finally what is happening, we are getting the change in the phase angle is nothing but 1/2 alpha t square. Now the deviation from the nominal speed, what we are trying to do, this change is nothing but it is, we can see here 1/delta, we have to derivate this, means change in the angle divided by dt, and if you are derivating this, you are getting this. So we are getting the change in speed is nothing but your alpha t. Or we can also, if you remember, I said here omega is nothing but your omega naught plus alpha t. You will take this side, so omega minus omega naught, that will be equal to your alpha t, and this is nothing but your change in omega. So we also get the same thing from that expression, and also we can derive from here this expression. So this is equally valid, and this is the equation, means change in angular speed is nothing but your time multiplied by your acceleration, angular acceleration, this I am talking. We also had the one relation that t net is nothing but your I, that is angular, here I is your moment of inertia and alpha is your angular acceleration, that we can multiply together. So we are getting this. Now this alpha is nothing, here you can say what is alpha? Alpha is omega upon here t. So I can say here alpha is nothing but your change in omega over change in time. So we can write here I into the change in speed over change with the time, and we can get this. And if you will put here this value omega in this reference here, we can get I multiplied by the double differentiation of change in phase angle delta. So we are getting one relation here, this means in the simple way I can say here I into d square over dt square, change in phase angle will be equal to your t net. Now here just we have derived in the change in angle, this is very good. We want to here see the change, that is the t net from your the reference setting, means here this we have a p net. P net is nothing but your, I can say the P mechanical minus your P electrical, or in similar fashion I can say this T net is nothing but your T mechanical, yeah, of course, minus T electrical, means here this T net is the difference between mechanical and electrical, and the power net is your mechanical, P mechanical minus P electrical. We know that this during this initial case, this I can say it is nothing but your P net at the where this reference axle we are talking, plus some change in P net, or we can say how much this we are changing from one value to another value. So this is your P net, that we are changing the P net we are getting, but the P mechanical is equal to your P mechanical naught, which was earlier, plus your P mechanical, or in other words I can say here we can derive this expression. I can use some space here. What is happening? As I said, your this P net, it is, as I said, your P mechanical minus P electrical, and we know that this P mechanical I can write is equal to your P mechanical, that is during the steady state, minus plus change in P mechanical. Similarly, we can write this P electrical is equal to your P electrical naught plus change in P electrical. So what happens if you want to calculate this change in P net? If you put these values here and as here, so you will get the change in the P net, that's the real power, will be change in the mechanical power from the naught value, from the steady state value, from the during steady state value that I am talking. So this minus here they are change in the P electrical value. So also this P net, since we have a change in the T net, means the oscillating power has changed, means it is not 0, so the speed will change, and the speed will change from your omega naught. So omega naught plus change in speed, that will be multiplied by your T net, that is which is the difference between the T mechanical minus T electrical, and thus here we can define it. So the P net will be the multiplication of this factor multiplied by the T net, and this T net is nothing but your T net naught, that is your the in steady state T net, and in steady state it was 0 because the mechanical was completely equal to your electrical if we ignore the losses. So that plus change in the T net, how much that is changing, and that T net change is nothing but your T net change in the mechanical minus change in T electrical. So if we will simplify this, means P net can be also written in the P net naught plus change in P net, that will be equal to, you can multiply here, so you will get the omega naught, this factor is multiplied by this factor, so this is this factor multiplied by this factor will get this factor, this omega will be, change in omega is multiplied by the here this factor, we are getting this another one, and omega naught if multiplied by the change in the T net, we are getting this factor. So we will expand this, we will get the 4 terms. Now what is T net naught? T net naught or P net naught, they are 0. Why? I have written here. Because in the steady state, what was this P mechanical was equal to your P electrical. So this net is 0. So here the change in the P net at the naught in steady state it was 0. Similarly, this T net will be also 0, because if P is 0, the T will be 0 because the P is related with omega. So if you put these values, so what will happen? This will be your cancelled out, this will be your cancelled out, and this will be your cancelled out. So what you are getting? You are getting change in P net, that will be equal to your this term omega naught into the T net plus here you are getting omega into change in T net. So you are getting 2 terms. Now change in the P net, normally you can say this term is very very small and this is also small. So we are just changing a speed change multiplied by change in the net, so this value is very small. So normally we ignore this one also because this is having very less impact, because this value is very fraction. So we can ignore and we can put it 0. Here already I have put 0, here 0, here it is 0. So we are getting the relation, the change in P net here, that will be equal to the omega naught, that is the base speed, multiplied by the change in T net. So from this equation here already I have used this one. You can see this P net change in mechanical power minus change in electrical power, here we have written, that will be equal to your omega naught, and this is nothing but T net is your change in mechanical torque minus change in electrical torque, and we are having this expression. Now here what we are going to relate these terms with our previous one. Here our intention is to relate in the T net form here. So to see that, now T net, what is the T net will be? T net is the T mechanical minus T electrical torques. That will be here this mechanical plus change in the mechanical, and here minus torque electrical not at the base case plus change in the T electrical. What is happening? This and this will be cancelled out because they are in a steady state case, both are equal. So we are getting T mechanical, here is this change in T electrical. So here this what we are getting, this is nothing but your T net. So this we can write the T net now from our the previous equation here, this T net, that is equal to, I can write here this expression, or we can say here this change in this, or you can say T net will be equal to I into d upon dt change in omega. So again we can simplify here. From equation star, I can say this change in the mechanical power. Now I am writing in terms of power, because all the quantity we represented in the power rather than torque. In the power system, it is the torque has no meaning because it's very difficult to calculate the things in the torque. It is better to go in the megawatts and the frequency terms so that we can easily solve the problem. So here the change in the mechanical and change in electrical powers, that will be equal to, here I have multiplied this, and this is your nothing but the T net. So here omega naught is multiplied, and then omega naught into I is nothing but it is your m, that is your angular momentum. So now I can see here we are having expression that m d over dt change in omega, that will be equal to your change in P mechanical minus change in P electrical. So this P mechanical, what is this? This P mechanical is nothing but your turbine output. So this is your turbine output that is coming, and if you are taking here the Laplace transform of this expression, we can have in the S domain change in the mechanical power in the S domain minus change in electrical power in S domain, that will be equal to m, that is angular momentum, multiplied here the differentiation is there, so S term will be appearing into change in omega S. So what we are getting? We are getting here the expression for this, we can write in the transfer function. Here you can see the change in the mechanical, and that change in mechanical power is nothing but the output of the turbine, that is a change in PT which we used in the modeling of the turbine. Minus here the change in electrical. What is the change in electrical power? It is nothing but that is a load on the alternator. So that is also is related with the change in PL. We will see later on this PL is not directly this electrical, there is some damping also. So approximately we can say it is equal to the PL. And that is coming to here is 1 over S. If it is multiplied, then we will get the change in here the speed. We also get one relation, very carefully. What we had this change in omega is nothing but it is your d over dt change in delta. So if you want to write here omega S, that is nothing but your S into change in delta S. Or here what we can do, if you want to write in terms of delta, so this is multiplied by I can say delta S, here I can say it is 1 upon S. So here we want to go for even though delta terms also we can get it, but our concern here is the frequency rather than delta. So this is nothing but your change in omega is nothing but your change in frequency. Both are same thing, there is no difference. So here I can write here this omega S change always. Here it will be your change in the frequency if you are using in the per unit system. If you are not using the per unit system, then this omega is radian per second, it is in hertz, both are different. We will see some problem how we can going to relate it. Now we have to now combine all these models. Models means model of governor, turbine and this generator. Let us see what we are going to have. Now we had here, if you remember, here it was your the PC, that was coming your change in the PCS. Here it was positive. Then we had some here the term with the negative, and we had some drooping characteristic, that is 1 upon are with the negative sign, and here it was coming your change in Fs. Now this was coming and it was coming to the governor. So now the governor time constant, and I have to now write the governor and the turbine together because I said that kg multiplied by kt is kept unity. So both now coming together. So I can write 1 here kg into kt. I can write 1 plus tg, that is a governor time constant, yes, here 1 plus your tt, yes, here of your turbine, and here we are getting your change in pt, and that change in pt is nothing but is a change in mechanical power, and here again we are going to add this, and here we are getting change in, this is your plus, this is minus, and this is nothing but your change in the load, means change in electrical power, and then here we are getting a term 1 over ms, and here we are getting change in omega s. So this is the model that we are going to get. This is also related with the change in the frequency if we are changing the unit. So this frequency here is nothing but is coming here. So the value here, the change in the frequency, if you are using in the per unit, this change in here will be there. Otherwise you have to change with some constant here k, and then it is fed to this, means omega is related to your frequency, and then it is a loop. Now you can see this is a loop, and we have to go for the solving, and you have to see the system, and this is normally called this primary control, and we will see other secondary and tertiary controls later on. But here this load is not constant, it is also affected by the change in frequency. In the power system there are various loads, they are also changed if the frequency is changed. How? For example, let us suppose your induction machine is there, and once the frequency is changed, its torque is reduced, even the torque is changed, and once the torque is changed means the output of that machine is changed. So we have to model the system, we have some damping coefficient, that is d, that is related with your frequency and then your this load. So we have to relate the frequency and this electrical load with that, and then we will see how much we are going. So that's why I said here it is nothing but it is approximately. So we will see this, we will try to model that this change in, that is a change in P electrical. Here it is your change in the load plus some other factor, and that basically the modeling of load will give the system here. Now let us see in the power system there is not only one generator, there are so many generators. So and they are having the different R characteristic, that is regulation constants. R will be the different for the different. How they will share the load if they are operating in the parallel. To see this, as I said, the characteristic that we can draw here, this is a load, that is a P that's there of generator 1, that is you can say PG1, and another generator here, it is I can say PG2. Now one generator is having this slope, this is very deep, and another is having very less slope. So what happens, let's suppose they are operating here at the sum, this is the frequency, operation frequency here, and since they are connected parallelly, so the operation of the frequency will be same. And let us take this is your F0, that is the nominal frequency, means they are operating at the rated frequency. So the loading of this generator will be nothing but this will be sharing here P1, and this will be sharing your load P2. Now you can also see here, those are having here this less slope, those are loaded much, means they are taking more load here from, you can say, from 0. Now if there is a suddenly release in the load, or you can say let us we put more load on the system, is very important. I change a change in the loading, that's electrical power, just we have increased this value, just it is a positive. What will happen? Means now that load must be shared by these two generators. So and they must share in such a fashion that steady state frequency is again the constant, and that it will be fixed, and it will be of course the lower than that because the power is increased. So what will happen here, you can see now let us suppose here this frequency has set and that will be parallel. Here it is some value f prime. Now you can see this will be changed from here P1 to P1 prime. Here this will be changed from P2 to P2 prime. So the change in the loading means that is the difference here in the P1 prime minus P1 plus that is your P2 prime minus P2, that is nothing but your change in the load which has been taken place. So this change in the here output of 1, change in the output, it is nothing but here I can say change in Pg1 plus change in Pg2. So you can see here this generator is sharing more compared to this one. So those are having here less slope, it will be loaded much compared to this. So this is the parallel combination of this machine. So you can see here this is similarly we can go for if load is released, means some loads are set off, then frequency will rise from this nominal. Here this is your nominal frequency, the side out. Here we are starting from 0 here. So the sharing also here the system frequency will be constant, and then we'll have that system frequency. Based on that we can calculate what will be the loading of the system and generators, that and they will take care of that. So you can see the change in here from P1 to P1 prime, and here it is changed from P2 to P2 prime. So this is the load, that is if it is increased, so this value that they have to go for. If reduced, then we can also similarly what will happen if this is a negative. Means we have reduced the load, what will happen? System frequency will go up, and you can see here f double prime. What will happen? The now net release you can say here, now we are getting here P1 double prime, and here we are having P2 double prime. So we have again you can say now we have shifted, means we have reduced the loading here and from here to here, and you can see that the reduction of load in this case is in two cases it is much higher than your this case. So this is your frequency rise, and again we can write your this change in now PL, that is negative. It is nothing but how much we are going for. This is here P1 minus P1, P1 minus here P1. Again here this will be the negative, I can say this double prime minus P1 plus here P2 double prime minus P2. What will happen? Now this quantity will become negative, this will be negative, and finally the change in load is negative, means we are setting off the load. So this is the parallel combination of that. So in this lecture, now I can recap. In this lecture we saw the modeling of turbine, and however we used for this analysis purpose, or you can say simplicity, I have used only the turbine without the reheating. But if you are using some computers and other things, then you can use the detailed modeling. Later on also I will use the turbine modeling without reheating, so that we can see the performance of the system, or you can say the various loops, that is a load frequency control loops. I also model the generators along with the rotating mass of the turbine. So it is your generator plus turbine rotating mass, and then we related the turbine output to the electrical output, and that is electrical output related with the frequency of the system. And then I combined together all these two, and then we saw that the complete block diagram of governing system, which I discuss here the governing system in the lecture 1, governing, then turbine, here the load, and then we saw this performance. Another model is left out, that is your load model, which I will discuss in the next lecture, and then your complete one loop, that is a primary load frequency control loop, is completed, and then we'll add the load model as well, and then we'll have a complete this ALFC primary loop, and we'll see the performance, that is a steady state performance as well as the dynamic performance, and then we'll analyze the loops and we'll see what else are required for maintaining the frequency to its rated value. So we'll discuss in your next lecture. Thank you.